Suppose I told you that somewhere out there, right now, there is an object so strange that if you fell into it, you would be stretched like taffy, feet first, pulled apart atom by atom, and from the outside, nobody watching you would ever see you arrive. They would watch you fall and fall and fall, and you would just get slower and dimmer and redder until you faded out like an old photograph left in the sun. You never arrive. You never stop. You just asymptotically vanish. Now here is my question, and I want you to really sit with this. Which one of you is right? The person falling in, who hits the center in a perfectly finite amount of their own time, or the person watching from outside, who never sees them land? The answer is both of you, at the same time. And that is not a paradox. That is the universe telling you something true about the nature of time itself, something so strange and so gorgeous that when I first really understood it, and I mean really felt it in my bones, I had to sit down and laugh. So let's go there together. Let's go to the place where space ends and time does something nobody asked it to do. Let's talk about black holes. Now I want to start with something you think you already know. You have heard the phrase escape velocity. You have probably heard that the escape velocity of a black hole is greater than the speed of light, and that is why nothing can get out. That is true. But it is not the most interesting truth. It is like saying a great novel is made of ink. Technically correct, completely misses the point. So let me back up, way back, to a man named John Michell. John Michell. Most people have never heard of him. This is a shame, because in 1783, when people were still writing with feather quills, this English clergyman sat down and did a calculation. He was thinking about Newton's gravity, which we all know pulls things together, and he thought, light must have some mass, right? That was the assumption at the time, and if light has mass, then gravity should be able to pull on it. And if gravity pulls on it, then maybe, just maybe, you could have a star so massive that the escape velocity from its surface would exceed the speed of light. He called them dark stars. He wrote this up, sent it to the Royal Society, they published it, and then nothing happened for about 100 years. The world wasn't ready for that idea. It just sat there like a time bomb in an old journal. Then along came Einstein. And Einstein did something Michell couldn't do, because Newton's gravity was not the right tool for this job. Newton imagined gravity as a force, an invisible hand reaching across space, pulling mass toward mass. That picture works beautifully for most things. It will get you to the moon. It will let you predict where Jupiter will be in 50 years. But when things get very heavy or very fast, Newton starts to crack. And Einstein saw the crack. Einstein said, and this is the leap, this is the beautiful leap, gravity is not a force at all. Gravity is geometry. It is the shape of space and time. Mass curves space-time the way a bowling ball curves a rubber sheet. And what we call gravity is just things following the straightest possible paths through that curved geometry. This was 1915, the general theory of relativity, and it changed everything. Here is a thought experiment I love. Imagine you are in a rocket ship, far out in empty space, no planets nearby, nothing. The rocket engines fire. You feel yourself pushed into your seat. Now tell me, without looking out a window, are you accelerating in empty space, or are you sitting still on the surface of a planet with gravity pushing you into the chair? You cannot tell. There is no experiment you can do inside that rocket to distinguish the two cases. Einstein called this the equivalence principle, and he said, these two situations are not just similar, they are the same. Gravity and acceleration are the same thing looked at from different angles. That one insight, that one realization, is the seed from which everything else grows. So when mass curves space-time, what it's really doing is creating a region where the straight-ahead direction points toward the mass. If you are near the Earth and you let go of a ball, the ball doesn't get pulled down. The ball moves in the straightest line it can through curved space-time, and that straight line happens to curve toward the Earth. This is not a metaphor. This is what is actually happening. Now, what happens if you keep adding mass? If you keep curving space-time harder and harder and harder? At some point, and this is where it gets wild, the curvature becomes so extreme that the direction pointing toward the center becomes the only direction. Not just the easiest direction, the only direction. All paths, every possible path through space-time, begin to lead inward. And when that happens, you have a black hole. Carl Schwarzschild figured this out in 1916, 1 year after Einstein published general relativity. Here's the remarkable part. Schwarzschild was serving on the Russian front in World War I. He was in the trenches doing physics in his spare time because that is the kind of man he was. And he solved Einstein's equations exactly, on which Einstein himself hadn't fully done yet. And he found something extraordinary. There is a critical radius. For any mass, there is a sphere you could theoretically compress that mass into. And if you do, space-time curves so severely at that surface that it becomes a one-way door. Everything can go in. Nothing can come out. Not light, not information, not anything. We call that radius the Schwarzschild radius. For our sun and our entire sun, 1,000,000 times the mass of the Earth, the Schwarzschild radius is about 3 kilometers. 3 kilometers. The sun is 1.4 million kilometers across. You would have to compress the entire sun into a ball 6 kilometers wide. For the Earth, the Schwarzschild radius is about 9 millimeters, the size of a marble. I want you to feel that. All of the Earth, every mountain, every ocean, every city, every person who has ever lived, compressed to a marble, and the geometry of space around it becomes a trap. Schwarzschild sent his solution to Einstein, who wrote back that it was wonderful. And then Schwarzschild died just a few months later of an illness he contracted in the trenches. He never got to see what he had found. He never got to watch the world slowly realize what his equations meant. And for a long time, the world didn't want to believe it. The surface I described, that critical radius, got a name. We call it the event horizon. The event horizon is not a physical surface. This is important. You have probably imagined it like a wall or like the surface of a planet, some hard boundary you crash into. It is not like that. The event horizon is a location in space-time, a mathematical surface, beyond which no path leads outward. If you crossed it in a spaceship, you might not notice anything unusual at all in that instant. No wall, no alarm, no change in temperature. You might even look around and think nothing happened. But the geometry of the space-time you are now in has fundamentally changed. Every direction you can travel, every possible future available to you, leads inward. You are inside a region where the future only points one way. Now here is the moment I want to use to jolt you awake, because you might be getting comfortable. You might be nodding along thinking, okay, gravity, space-time curvature, event horizon. Got it? I follow. Stop. I want to ask you something. You have always thought of time as something that just flows. It flows forward at a steady rate, and maybe Einstein told us it can speed up or slow down depending on how fast you move or how strong the gravity is. Sure, okay, time dilation, we've heard that. But here is what the equations really say about a black hole. They say that near the event horizon, the slowing of time becomes infinite. The rate at which your clock ticks, as seen by someone far away, goes to zero. You never cross the horizon according to the outside observer's time. You fall slower and slower and slower, and the light you emit gets redshifted, stretched to longer and longer wavelengths until it is infrared, and then radio waves, and then wavelengths longer than the observable universe. You simply cease to arrive. But from your own frame of reference, from the inside of your falling spaceship, no such thing happens. You fall normally, cross the horizon in a perfectly finite amount of your proper time, and continue falling until something very unpleasant happens at the singularity. Both of these descriptions are correct. The physics of relativity does not say that one observer is right and the other is wrong. It says both are valid descriptions within their own reference frames. What I am telling you is that a single physical event, you falling into a black hole, can be honestly described in two completely different ways, and both are true, and they do not contradict each other because they describe what is seen from two different locations in a genuinely curved space-time. This is not philosophy. This is not wordplay. This is physics. And if you sit with that long enough, you start to realize that your intuitions about what really happens are being strained to the breaking point. And that is a good sign. Your intuitions were built for the African savanna. They were not built for the neighborhood of a stellar mass black hole. I am not embarrassed that the intuitions fail. I am thrilled. It means we've gone somewhere new. Let me tell you about spaghettification, because I love this word and the concept behind it is real. If you fall into a sufficiently small stellar mass black hole, say one that formed from a star about 10 times the mass of our sun, the difference in gravitational pull between your feet and your head as you approach the singularity grows to be enormous. Your feet are closer to the center. The tidal force, the differential gravitational pull, stretches you vertically and compresses you laterally, and it does this with increasing ferocity as you fall. You are stretched like taffy. Your atoms are pulled apart from one another. You become, in the most literal physical sense, a thin stream of particles falling toward the center. The astronomers, I love that they did this, the astronomers gave this process a name, and the name is spaghettification. Now here is the funny thing. The larger the black hole, the gentler the tidal forces at the horizon. At the event horizon of a supermassive black hole, like the one at the center of our galaxy, which is 4 million times the mass of the Sun, the tidal forces are actually quite mild. You would cross the horizon without any discomfort at all. You would not be spaghettified at the horizon. The spaghettification happens later, much closer to the singularity. So if you want to survive as long as possible inside a black hole, which I want to be clear is not survivable in the end, you want a big one. The irony is that the more terrifying the object, the gentler the door. But wait, I haven't told you the really strange part yet, because all of this and the falling, the tidal forces, the event horizon, the geometry, all of this assumes the black hole just sits there. But black holes don't just sit there. In 1974, Stephen Hawking did something astonishing. He combined quantum mechanics with general relativity in a calculation that still makes physicists wince with how difficult it is, and he found something nobody expected. Black holes glow. Let me say that again. Black holes, objects from which nothing can escape, radiate. They emit thermal radiation. Not much, usually. For a stellar mass black hole, the temperature is a fraction of a millionth of a degree above absolute zero. The cosmic microwave background radiation, the leftover glow from the Big Bang, is far hotter than any black hole we know of. So you would not detect this glow directly. But mathematically, the glow is real, and it has extraordinary consequences. Here is how to think about it, and I want to be careful because this analogy will mislead you slightly, but it is better than nothing. In quantum mechanics, the vacuum of empty space is not empty. It is full of what we call virtual particles, pairs of particles and antiparticles that spontaneously pop into existence together, exist for an unimaginably tiny moment, and then annihilate each other and disappear. The energy they borrow from the vacuum is paid back almost instantly, so the accounting balances and energy is conserved. This is real. The Casimir effect measures it directly. Now, right at the event horizon of a black hole, one of these virtual pairs can be separated by the horizon. One particle falls in, and the other escapes. The one that escapes becomes real. It carries real energy away from the black hole. And where does that energy come from? It comes from the mass of the black hole itself. The black hole gets ever so slightly lighter. One particle at a time, over an almost incomprehensibly long time, the black hole radiates energy and loses mass. And as it gets smaller, the radiation rate goes up. And eventually, after a time so long, I can barely write the number. Something like 10 to the power of 67 years for a stellar mass black hole. It evaporates completely. A final burst of radiation, and it is gone. But here is the problem. Here is the thing that is not solved. The radiation Hawking found is thermal radiation. It is random. It carries no information about what fell in. If you threw a copy of Shakespeare's complete works into a black hole and waited for the Hawking radiation to come out, the radiation would carry no record of what was in the book. The information, the specific arrangement of atoms that made those particular words, appears to be destroyed. This is deeply upsetting to physicists, not because it hurts our feelings, but because quantum mechanics, our very successful theory of the very small, says that information cannot be destroyed. Quantum evolution is reversible. If you know the exact quantum state of a system now, you can, in principle, work backwards to reconstruct any prior state perfectly. But if black holes destroy information, quantum mechanics is wrong. And if Hawking radiation doesn't destroy information, something is terribly wrong with how we have been thinking about the event horizon and space-time and quantum mechanics together. This is called the black hole information paradox. It has been one of the central unsolved problems in theoretical physics for 50 years. People have thought about it from every angle. Leonard Susskind wrote an entire book about an argument he had with Stephen Hawking about it, a book he titled The Black Hole War, which is my kind of title. Hawking eventually conceded after many years that information is probably not lost, that it must somehow be encoded in the Hawking radiation in subtle correlations that we do not yet understand. But we do not know exactly how. We do not have a theory that makes all the pieces fit together without something breaking. And I want to be honest with you, that I find this thrilling, not frightening, thrilling, because it means the universe has not finished with us yet. We have not figured everything out. The fact that two of our best and most successful theories, quantum mechanics and general relativity, disagree about what happens to information in a black hole means one of them is incomplete, or both of them are, and a deeper theory is waiting to be found. Some people call this quantum gravity. Some people call it string theory. Some people call it loop quantum gravity. We do not have it yet, but the clue is sitting there in the black hole information paradox, waiting. The physicist John Wheeler, who actually coined the term black hole in 1967, had a phrase he loved. He said, "It from bit." He meant that at the deepest level, the physical universe might be made not of matter and energy, but of information. The universe might be, in some sense, a computation. A bit flips and a particle exists. A bit flips back and it doesn't. This is a strange idea, and I am not sure it is right, but I am not sure it is wrong either, and it is exactly the kind of idea that black holes force us to take seriously. When you have an object that seems to erase information from the universe, you have to ask, what is information, really? Is it a property of particles? Is it fundamental? Is it what the universe is made of? I do not know the answer. Wheeler did not know the answer. Nobody knows the answer, and I say that with enormous enthusiasm. Now let me tell you about gravitational waves, because this story changed everything just a few years ago. Einstein's equations predicted that when massive objects accelerate, when two black holes orbit each other and spiral inward and merge, they should send ripples through space-time itself, not through space, through space-time. The fabric itself oscillates, squeezing and stretching in perpendicular directions as the wave passes through. A passing gravitational wave would alternately stretch you left to right and compress you top to bottom, then vice versa, faster than you could perceive it. And the stretching is incredibly tiny for the gravitational waves we can detect, the stretching of 4 kilometers of space by less than 1,000th the width of a proton. So measuring this seemed, for a long time, impossible. Einstein himself doubted we would ever detect them. He thought nature was too subtle. Then in 2015, September 14th, 2015, at 5:51 in the morning Eastern Time, two black holes, roughly 36 and 29 times the mass of our Sun, finished a billion-year inspiral and crashed together in about a fifth of a second. In that fifth of a second, they radiated more energy in gravitational waves than the light output of every star in the observable universe combined, and LIGO, the Laser Interferometer Gravitational Wave Observatory, felt it. The instrument squeezed and stretched by that inconceivably tiny amount, and the computers caught it, and the scientists ran it through their algorithms, and they found a signal that matched exactly what general relativity predicted for a black hole merger. They heard, and I am using the word honestly because they converted the gravitational wave signal into sound, they heard two black holes collide. It sounds like a chirp, a brief rising note. 130 years after Michell imagined dark stars, 100 years after Einstein wrote down the equations, we heard the universe do something no human had ever heard before. I get goosebumps. Not because it is terrifying, because it is so unbelievably beautiful. The signal they detected is called GW150914, and it is arguably the most important detection in the history of observational physics. Not because of what it destroyed, but because of what it confirmed. It confirmed that black holes exist as binary systems. It confirmed that they merge. It confirmed the shape of the waveform, the exact way the chirp sounds, which encodes the masses, the spins, and the final ring-down of the merged black hole. It confirmed general relativity in a regime we had never tested before, a regime of extreme curvature and violent dynamics. And it opened an entirely new way of listening to the universe, a new sense we have given ourselves, a new astronomy that does not use light but uses the trembling of space-time itself. We have since detected dozens more: neutron stars merging, black holes of unexpected masses, an event that lit up in gamma rays and visible light and gravitational waves simultaneously, letting us pin down the source to a single galaxy, a single patch of sky, We are right now in the early days of gravitational wave astronomy, and I suspect that what we will find as we get better at listening will astonish us in ways we cannot yet predict. Now let me come back to the singularity, because I have been dancing around it, and you deserve to know the truth. At the center of a black hole, or wherever the infalling material ultimately ends up, which is a question that is genuinely open, the equations predict a singularity, a point of infinite density, infinite curvature, a place where the equations break down, where they give you infinity as an answer, which is physics' way of saying, we don't know what happens here. The theory has failed. What does infinite density actually mean physically? Almost certainly nothing. Almost certainly it means that general relativity is incomplete, and that in the extreme conditions near the singularity, quantum effects become important in a way we do not yet know how to handle. The singularity is not a place where matter actually becomes infinitely dense. It is a signpost that says, beyond this point, a better theory is required. Roger Penrose and Stephen Hawking proved, using a set of theorems that are genuinely beautiful pieces of mathematics, that singularities are inevitable inside black holes given certain conditions. But inevitable according to general relativity might just mean here is where general relativity stops being the right tool. We don't know what is really there. We don't know what the final theory will say about the center. And here is a thought that I find somewhat humbling. The center of a black hole may be the only place in the universe, the only place where you would be forced to confront quantum gravity directly, with no escape from the extreme conditions. It is the universe's own laboratory for testing the deepest possible physics. And we cannot get there. We cannot look there. The event horizon protects the singularity from us, hides it behind a barrier we cannot observe through. Roger Penrose has a conjecture he calls cosmic censorship, the idea that singularities are always hidden inside event horizons, always invisible to the outside universe, always censored from our view. If this is right, it might be nature's way of keeping its unfinished business private. The places where the theory fails are the places we are not allowed to look. If that doesn't give you the feeling that the universe has a personality, I don't know what will. Let me talk for a moment about the supermassive black holes, because when I say supermassive, I don't want you to nod vaguely. I want you to feel the scale. At the center of virtually every large galaxy, including our own Milky Way, there is a black hole with a mass of millions or billions of solar masses. Millions. Our own galactic center has one called Sagittarius A, and it has a mass of about 4 million suns. 4 million suns compressed into a region smaller than our solar system. And we have actually imaged it, or rather, we have imaged its shadow. The Event Horizon Telescope, a collaboration of radio telescopes scattered across the entire Earth, working together as a single instrument the size of our planet, produced an image in 2019, and then a sharper image of Sagittarius A in 2022, showing the dark shadow of the event horizon against the glowing ring of infalling hot gas. A photograph of a black hole. We have a photograph of a black hole. I look at that photograph and I see human beings at their best. I see people who decided that a thing which seemed impossible, imaging an object millions of light years away with an angular size so small that you need a telescope the size of the Earth, was worth trying to do. And they did it by stitching together radio telescopes in Chile and Hawaii and Spain and Antarctica and combining their signals with incredible precision. And they got a picture. A blurry, orange-ringed, extraordinary picture. And there it was. The thing that John Michell imagined in 1783 with a feather quill was there on a computer screen. There is something I need to say about the word destroy, because the title I've been given for this talk is How Black Holes Destroy Everything, and I want to push back on that word a little. Push back gently, because in one sense it is correct. Matter falls in and does not come out. And in that sense, the black hole destroys things. But physics tells us something more subtle. Nothing is truly destroyed. The matter that falls in contributes to the mass energy of the black hole. The Hawking radiation that eventually carries that mass energy away, even if we don't understand exactly how it carries the information, carries the energy out eventually. The black hole converts mass into radiation. It is a transformer, not a destroyer. Over unimaginable timescales, the mass that fell in comes back out as thermal radiation, and the universe is slightly different, and entropy has increased, but nothing, no energy, no information, in the final accounting, has been created from nothing or destroyed from something. The conservation laws hold. They must hold. That is not blind faith. That is the deepest conviction of physics based on every test ever conducted. What I am saying is, the universe does not destroy, it transforms. Even in the most extreme, most violent, most seemingly terminal object we know, a black hole, what is really happening is transformation. Mass to radiation, structure to heat, the particular to the general. It is terrifying only if you think that the particular arrangements of atoms matter more than the underlying physics. But the physics says the dance continues, the forms change, the dance continues. And now I want to tell you the thing I think about when I really sit alone with all of this. We have, in the history of human civilization, developed the ability to not just observe the universe, but to understand it. To sit in a room with a pencil and some paper and write down equations that tell you what happens at the edge of the most extreme object in the universe. Equations that predicted, correctly before any observation confirmed it, the existence of gravitational waves, the shape of the black hole shadow, the precise sound of two black holes colliding 1 billion years ago and 1 billion light years away. That is remarkable. That is, if you step back from it and really look at it, almost impossibly remarkable. Why should the universe be comprehensible? Why should mathematics, invented in human heads for the purpose of counting sheep and calculating taxes, why should it turn out to be the language of space-time curvature and quantum fields? I don't know. Nobody knows. Eugene Wigner called it the unreasonable effectiveness of mathematics, and he was right that it is unreasonable and right that it is effective and right that it demands explanation. And I will be honest with you and tell you that I have no good explanation. But here is what I believe. I believe the fact that the universe is comprehensible, the fact that we can sit here and talk about what happens inside an event horizon using nothing but thought and mathematics, is the most important thing about the universe, more important than its size, more important than its age, more important than the black holes and the galaxies and the billions of years of stellar evolution. The most important fact about the universe is that there exist inside it creatures who can ask, "What is the universe?" and get not a perfect answer, not a final answer, but a real answer, a working answer, an answer that makes predictions that come true. We are, as far as we know, the universe looking at itself, and what it sees when it looks through us, what it finds at the edge of its own most extreme structures, is not chaos, not meaninglessness. It finds geometry, it finds elegance, it finds the Schwarzschild radius and the Penrose process and Hawking radiation and the beautiful, haunting chirp of two black holes becoming one, rippling across 1 billion light-years of space-time to make a tiny instrument tremble in the Louisiana bayou. That is the thing about black holes that no one tells you. We spend all this time saying they destroy, they consume, they are the great devourers. But what they have given us, what they have taught us, is that the universe is, at its deepest level, mathematical. That space and time are not fixed, they are dynamical. That matter curves geometry, and geometry guides matter. That two black holes spiraling together for 1 billion years will sing a song whose lyrics are Newton and Einstein and Hawking and 1,000 other people who spent their lives paying attention. The hole in space that destroys everything has taught us more about the structure of reality than almost anything else we have ever found. So let me ask you to leave here with a question. Not the question of whether black holes are terrifying. They are, and they are also sublime. Not the question of whether we will ever understand quantum gravity. We will try, and we might succeed, and we might find something even stranger. The question I want you to carry home is this: why does any of it work? Why do the equations come out right? Why does a man in a trench in World War I, solving a problem in general relativity as the artillery fires, find an answer that matches a gravitational wave detector 100 years later? Why does the universe cooperate with our mathematics at all? I don't know. But I can tell you this: the fact that we are here, asking that question in a universe that keeps answering, that to me is not frightening. That is the opposite of frightening. That is the most hopeful thing I have ever encountered.